Alright, welcome to One Sample T-Test. We're going to be talking about samples and populations, null and alternative hypothesis, type 1 and type 2 errors, which will be a refresher from last lecture, alpha, beta, and power. We'll talk about the z-test as compared to the t-test, and we'll talk about how to calculate the t-test, how to calculate the p-value, which, hint, we don't. We actually get it through a program called SPSS, and the difference between one and two-tailed, as well as critical values, assumptions, and how to look things up. Alright, so let's take a look at hypothesis testing. Hypothesis testing is seeing if something which is called the null relates to what's going to be the alternative, and we're looking to reject the null. Think about it, as you get older, you reject Santa. H-O is like Santa Claus, ho ho ho. And the alternative is you look back and you think it's funny that you believed in Santa Claus. Now notice here we've got equals, not equals. This not equals indicates that it is going to be what's called a two-tailed, which means you can either have more red or more black and still disprove this. And still disprove this part up here. Same thing goes down for here. We're comparing the average student's IQ versus that of the population. Student's IQ could be higher or lower, which would then make this statement true and this statement false. Now it's important to note that we are just looking to disprove Santa Claus, but we can't prove the alternative. We're just finding support. So we have the one-tailed, which is used when we predict a direction, greater, less than, more than, which has these indicator words and influencer words, which will tell us which way to look. Two-tailed non-directional means that it only predicts a difference but not a specific direction. Two-tailed is the most common. One-tailed is more uncommon, but it gives us more power, it gives us more ability to detect if something is actually different. Alright, let's take a look at this. This table down here tells us what's going on. So we have a two-tail, one tail if we're looking for greater, one tail less than, and it shows us what the symbols are going to go in up here. And it's sort of just plug and play. The null, if it's a two-tailed, always has an equal, and then a not equal for the alternative. If it's greater than, we have the less than or equal to as the null, and then the greater than for the alternative. If the is indicating less than, then the null is going to be greater than or equal to for the sign, and then the alternative is going to show less than. Alright, let's take a look at our different types of errors. Type 1 error is measured by alpha. Alpha is going to be given to us always. So the higher our alpha, the greater our type 1 error. Lower our alpha, lower our type 1 error. Our type 2 error is calculated by beta. However, for this class, we are not going to be discussing on how to actually calculate beta. Power is the ability to reject the null when it is indeed false. There are a few things that influence power, such as alpha, sample size, and whether it is a one-tailed or a two-tailed test. So let's take a look at a z-test example. Questions: do any IU psychology majors have higher IQs than that of the general population? So notice it says higher, which means the alternative is going to show greater than, or the alligator going towards it, or there's more room between the lines. However you remember it, that's how greater works, which means that less than or equal to is going to be our null. Just a reminder, sometimes I will use M as X bar. Alright, our formula. Z equals X bar minus mu. Now notice down here we have something new. We're putting an X. That stands for an individual score. For us now, we're going to be using what's called the standard error of the mean. And so that's going to go underneath instead of the standard deviation. And it's equal to the standard deviation over the square root of our sample size. Let's go to an example. All right, so here we go. We've got mean population equals 100 and the standard deviation of the population, which means we can use a z-test. If we don't have the standard deviation of the population, we have to use what's called a t-test. The mean for NEIU is 103.5. The sample size is 75. All right, so first steps first, we need to calculate the standard error of the mean. So that's going to be 15 from here divided by the square root of 75 over 1 point, which will equal 1.73. We take this value and then plug it into our z-score, which used to look like x, but now we're doing x bar. So it's still an individual mean or individual score subtracted from the population. We divide it by the standard error of the mean. So it's going to be 103.5 minus 100, 103.5, 100, divided by 1.73, which is our standard error of the mean, which will give us a value of 2.02. This is going to be called our z obtained. We then will compare that to something like z critical. In this case, our z critical is going to be 1.645. Since it is greater than 1.645, we are going to reject the null. So what we're going to do is we're going to draw out, and since it's one-tailed, we only have one rejection region. And it's going to be over here. We know from before that our rejection region is going to be 1.645, which means that anything to the right of it is going to be greater. So anything greater than 1.645 is going to fall there. We ended up with 2.02, hence we reject the null. More about critical values. It's the smallest absolute value of z that will allow you to reject the null hypothesis. For a one-tailed, it's 1.645 if it's a greater than. If it's a less than, then it's negative 1.645. Two-tailed, it's going to be 1.96. Now, if we have to reject the null for using SPSS, we're going to do p is less than 0.05. We will be given p only through SPSS. But this is the second rule. These two rules make up about 10 to 20% of your grade. Here is examples, a little better drawn out, about critical regions. So notice negative 1.645. The null is always going to be 0 in terms of the mean. So 0, 0, 0. So anything, if we're saying it's less than negative 1.645, when our tail that we assign through our null is less than, anything less than negative 1.645 would cause us to reject the null. Over here, anything greater. And here, any value that has an absolute value of greater than 1.96 would cause us to reject the null. All right, so assumptions for a z-test. Data are an interval or ratio scale. Population, mean, and standard deviation are known. Data are normally distributed. And we take apart the central limit theorem because that helps us if we don't have normally distributed data. As long as our n is greater than 30, we are good to go. All right, confidence interval gives us a range of scores, hence interval. So it's going to be the mean plus or minus the z critical. Now it's important to note, for confidence intervals, you always use the two-tailed. Always use the two-tailed. Always use the two-tailed times the standard error of the mean. So in our case, we're going to use 1.96, even though we just did a one-tailed test. So it's going to be 103.5 plus or minus 1.96 times 1.73, which will give us 103.5 plus or minus 3.39, and then we end up with 100.1 to 106.9. All right, let's compare z-test to t-test. Z-test assumptions. Data are on an interval or ratio scale, same as t-test. Population, mean, and standard deviation are known. However, with t-test, population mean is known, but the sample is known and not the population standard deviation. Data are normally distributed. Population data are normally distributed. Sample data are not. With the t-distribution, we'll go through in class. In the t-table, I'll show you that as we end up with more and more people, more and more degrees of freedom, it becomes more and more normal. What happens here is if you look at this, the red, which has less, all of a sudden becomes higher up, which means there's more area, because probability is defined by the area underneath the curve. Here's a comparison of z versus t in terms of the formulas. T is used when you don't know population standard deviation, or n is less than 30. T equals x bar minus mu. Notice here, same thing. Standard error of the mean, standard error of the mean. Standard deviation of x, standard deviation of x, square root of n, square root of n. Same thing. Here, though, the t critical depends on the degrees of freedom for n minus 1. We will look this up in the table together. There is a table in the back of your book. You can feel free to take a look at it. In this case, let's say we had 20 people. Our degrees of freedom would be 19. And we would use an alpha default of 0.05. And you need to know whether it's one-tailed or two-tailed. So again, in order to look up t critical, you need three things. Here we go, finding the critical value for t, alpha, one or two-tailed, and degrees of freedom. Again, alpha, which will be given to you, one or two-tailed, degrees of freedom. So let's run through an example based on a t-test. Notice here we're given S, which means that it's not going to be a z-test. We're looking at the average amount of hours that an NEIU student watches TV or screen time per week, 12.51, and compare it to the population, which we're just going to assume is 18. So we have m equals 12.51, standard deviation equals 10.44, n equals 39. So 10.44 over 39, because this is our standard deviation over our square root of n, gives us 1.67. Then we take our sample mean minus our population mean, and then divide it by our standard error of the mean, which will give us negative 3.29. Now if we look up in the back of the book, we will see that we have a degrees of freedom of 38, because n, which is 39 minus 1, gives us 38. We're looking at 0.05 and then a one-tailed test, so it should give us 2.021. Let's take a look at this. Rule 2 is what we're going to use. If the obtained statistic falls in the critical region, and all we need to do is just draw it out. Big thing here is just draw out a normal distribution. Put 0 in the middle. Put the absolute value, or the critical value, on the left or the right, depending where it goes, whether it's one-tailed or two-tailed. If it's two-tailed, it goes on both. If it's positive or negative. And then we mark out where the value that we obtained goes. And if the obtained statistic falls in the critical region, we will reject it. In this case, it would fall in the critical region, so we reject it. Confidence interval for the mean. Notice this says mean is exactly the same as what we did for the z. Mean plus or minus t critical. So instead of z critical, we're using t. And remember here, just like before, we're using two-tailed times the standard error of the mean. It's going to be 12.51 plus or minus 2.042 times 1.67, which gives us 12.51 plus or minus 3.41, which goes from 9.10 to 15.92. That's for the mean. Confidence interval for the difference. Now notice we're saying difference. Difference indicates subtraction. So it's going to be the sample mean minus the population mean with the same information here that we had up here. So it's going to be 12.51 minus 18 plus or minus 3.41, which will give us negative 8.9 to negative 2.08. Notice it doesn't actually include 0, which is an indicator that it is significant. All right, let's do this. This is now how we write things in APA style. Notice we've got t, degrees of freedom, equals t obtained, comma, p-value equals p-value. P equals p-value. So we get that from SPSS. And so to look like this, a one sample t-test showed that NEIU students, m equals 12.51, comma, 95%, confidence interval 9.13, 15.88, differed significantly from the population, t 38 equals negative 3.28. So that's what we had for t-test for the one sample. We're still going to cover two more. What we're going to do here is measure Pearson's R. It's the relationship between two variables from -1 to 1. 0 equals no relationship. We'll always use a two-tailed. This is not P, this is the Greek letter rho. Rho equals 0, meaning no relationship. Not equals 0, or significantly more, is the alternative. Degrees of freedom is n minus 2. The assumptions both variables are on an interval or ratio scale. Both samples are drawn from normally distributed populations. Here is how we do this in SPSS, APA style. R, degrees of freedom equals R obtained, comma, p-value equals p-value. The variable x and y weren't significantly correlated. R 55 equals 0.49, p less than 0.01. So again, we'll reject the null if the obtained value falls in the rejection region. Next we have up coefficient of determination, which is r squared, which all we do is just take r and square it. And this tells us the amount of variance in one variable that is associated with the other. Think about it like height, how much your parents' height influences your height or influenced your height. It's not perfect, so all the variability is not due to your parents. There's other factors such as how well you eat and other environmental factors that will play a role in it. Again, remember, reject the null if p is less than 0.05. Homework 3 is going to be due 1 week from today.